Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module, nuclear force and its properties, from paper Nuclear and Particle Physics. So students, let us see what we are going to learn in this module. The first thing that we are going to learn is the knowledge about the nuclear force. Second thing, the properties of nuclear force and their meaning. Third, the importance of deuteron case in understanding nuclear force. Now, nuclear force, which is also called strong interaction. Spin and parity of deuteron. So it means in this particular slide, we are going to study about the spin and parity of deuteron. From reaction studies and property of photon emitted, it has been found that the property of the ground state property of deuteron is basically positive. That is, parity is even. The total angular momentum I of the deuteron is given by I is equal to Sn plus Sp plus L. What is Sn? Sn is the intrinsic spin of the neutron, Sp is the intrinsic spin of proton, and L is the orbital angular momentum associated with proton. So now here on the right hand side in the picture, you can see that there are two possible combinations by which neutrons and protons can get combined. Neutron and proton within the deuteron nucleus can get combined. So here on the top one, you can see that the parallel combinations are given in which either both neutron and proton spins are downward, and in the second case, both neutron and proton spins are upward. There is another scenario. The another scenario can also happen when the neutron and proton are anti-parallel to each other. It means proton spin is down, neutron spin is up, proton spin is up, neutron spin is down. So these are the four possibilities in which neutron and proton can be there inside the nucleus. So now we will evaluate what their consequences are, means when they are in the parallel arrangement, when they are in the anti-parallel arrangement, what should be the spin of the nucleus. So Sn and Np, when they are parallel with L is equal to 0, means there is no orbital angular momentum as the proton is in S half state. So the second combination is Sn and Sp anti-parallel with I is equal to 1, because Sn and Sp combinedly will give half plus half is equal to 1, and L is again 0. Sn and Sp parallel with I is equal to 1, that is when Sn and Sp both are parallel, then they will give I is equal to 1, and the fourth combination is Sn and Sp parallel with I is equal to 2. So I is equal to 2 is under the assumption that there is a contribution from L also. Nuclear force, strong interaction. We are discussing the case of deuteron. Now for L is equal to 1, where L is the orbital quantum number, parity is equal to -1 to the power L, that is negative. Measured parity even, so not possible. For L is equal to 0 and 2, parity -1 to the power L is equal to positive. Measured parity is even, possible. It means in this case, because experimental values of spin and parity for deuterons are found to be positive, parity value for experimental parity for deuteron is found to be positive. So L is equal to 1 is not possible, and L is equal to 0, 2 are possible. So interaction potential is strongly spin dependent. Magnetic dipole moment of deuteron. So now we are going to discuss the magnetic dipole moment of the deuteron. Deuteron, as we know, is having two nucleons in the nucleus, one proton and one neutron with parallel spin. So magnetic moment of deuteron. If L is equal to 0 is a perfect description for deuteron, there should be no orbital contribution to the magnetic moment. So magnetic dipole moment of the deuteron is given by this expression. What does this mean? It states that if L is equal to 0 is a perfect description of deuteron, it means if we consider that the deuteron ground state has L is equal to 0, then mu L, because mu L is the magnetic dipole moment due to the orbital motion, has to be 0. So in that case, the total magnetic moment of the deuteron mu is equal to mu n plus mu p, that is equal to GSN mu n upon h bar Sn plus GSP mu n upon h bar Sp. Means if the orbital component, if we consider that the deuteron ground state has L is equal to 0, in that case the net magnetic moment of the deuteron will be equal to the sum of its spin components only, sum of spin components of neutron and proton only. And the expression is given by this one, where GSN is equal to minus 3.826084 and GSP is equal to 5.585691. These are the free nucleon or free neutron and proton G factors. Nuclear force strong interaction. We are continuing with our discussion about deuteron. As experimentally, mu is equal to mu z when spins have their maximum value, that is plus 1 by 2 h bar. So it means in the condition, because we define mu as equal to mu z, we know that by definition mu is equal to mu z in the state when m is equal to I. This we have seen in the definition of magnetic moment. So here also we would like to find the magnetic dipole moment, which is equal to mu z when the spins have their maximum value, that is ms is equal to I, and that is equal to plus h bar by 2, which is the maximum value of spin. Mu is given by 1 by 2 mu n GSN plus GSP, that is equal to 0.879804 mu n. So theoretically speaking, if we talk about the deuteron ground state as I is equal to 0, then mu has to be, if the deuteron ground state has L is equal to 0, then the mu should be 0.879804, whereas the experimental value is measured as 0.857436776 plus minus 0.000004 mu n. So observed value is found to be in good but not in exact agreement with the calculated values. So disagreement is seen between the measured value and the experimental value. So this agreement in the magnetic moment can be due to various reasons. One of the reason can be modifications in the internal structures of protons and neutrons in the bound state, so that Gp and Gn get different values than their free values. So one of the important point in disagreement can be that the Gp and Gn that we used in calculating the value of mu are different than their free values, because in the calculation we have used their free values, which are the maximum one, but when the nucleons are in the nuclear environment, they are not free, and so the Gn and Gs values will be different than their free values. But this situation is extremely unlikely, as deuteron is only a loosely bound system. So it means this possibility is very remote because of the fact that deuteron is only a loosely bound system. Hence protons and neutrons are not bound together very strongly, but they are more or less free. So nuclear force strong interaction. So we are continuing with our discussion about the spin and parity of deuteron. There are contributions from charge meson exchange between the proton and the neutron, and these have not been included. So it means in this case we have not included the interaction between the neutron and proton, because the neutron interaction between the neutron and proton is happening with the exchange of mesons between them. So far we have not included that exchange of mesons between the proton and neutron. So which is possible, as in fact it has been shown that mesonic currents are important in understanding magnetic dipole moment of odd mass nuclei. So at some point of time we have to consider this exchange of mesons, because it is in fact shown that mesonic currents are important in understanding magnetic dipole moment of odd mass nuclei. There is a small admixture of D3 state in deuteron, ground state, is more likely a major cause of discrepancy between mu d and mu d 3s1. So it means these are the conclusions that the people have drawn, since in the magnetic moment we see that the measured magnetic moment and the predicted magnetic moment are different or slightly different. So it indicates that there can be, so it indicates that our assumption about L is equal to 0 for the ground state of deuteron is not correct, and there is a small admixture of L values, other L values in the ground state of deuteron. As the experimental value of magnetic dipole moment of deuteron is very close to the calculated value, so admixture must be very small. It tells that since we have seen that the measured value and the expected value for magnetic moment are very close by, they differ only in the third and fourth digit after decimal. So we can say that even if there is an admixture of certain non-zero L values, then that admixture has to be very small. Nuclear force, strong interaction. So we have learned up to the previous slides that there can be an admixture of two states, that is L is equal to 0 and L is equal to 2 in the ground state of deuteron. So amount of admixture, that in what ratio the two states are mixed in the ground states, in the ground state of deuteron, that we are going to study here in this slide. That amount of admixture of 3d1 state for linear combination of 3s1 and 3d1 component. 3s1 component is because of the L is equal to 0 contribution, and 3d1 component is due to L is equal to 0, L is equal to 2 contribution. So for linear combination of 3s1 and 3d1 components, the deuteron wave function is given by psi is equal to as s1 plus ad plus ad d, with normalization condition that a square plus b square is equal to 1. A and b, as and ad are ratio of s component, amount of s component and amount of d component, or psi is equal to psi as psi L is equal to 0 plus ad psi L is equal to 2. Calculating the magnetic moment from this wave function, because we know that magnetic moment wave function is given by mu is equal to expectation value of mu z, that is psi mu z psi in the state when m is equal to I. So calculating the magnetic moment from this wave function, we get mu is equal to a square mu L is equal to 0 plus ad square mu L is equal to 2, that is equal to 0.857 mu n. The observed value is consistent with as square is equal to 0.96 and ad square is equal to 0.04. So what we have done here is, we have basically made the ground state wave function of deuteron, which includes the components from L is equal to 0 and L is equal to 2, and using this wave function which we have found, we have found the magnetic moment, expectation value of the magnetic moment, and equated that expectation value as equal to 0.857 mu n. Then going by the experimental values, because this 0.857 mu n was the experimental value, and then we found for what value of as and ad we can get this equation. So we observed that the values come out to be a square is equal to 0.96 and ad square is equal to 0.04. It means that in ground state of deuteron, there is a contribution of 96% of the L is equal to 0 state, and 4% contribution is from L is equal to 2 state. So in general, we can say that the ground state of deuteron is made up of, or is a combination of, L is equal to 0 and L is equal to 2 states. Nuclear force, strong interaction. So in the previous slide, we have seen that deuteron ground state is made up of L is equal to 0 and L is equal to 2 components. Now in this slide, we are going to study the what is the situation with electric quadrupole moment. Now the electric quadrupole moment, the measured value is Q is equal to 0.00288 plus minus 0.00002 barn. Now we must remember that the presence of quadrupole moment value for deuteron indicates that deuteron is deformed in the ground state. Now, as we define the magnetic dipole moment, in the similar way we define the electric quadrupole moment of a nucleus. The quadrupole moment of a nucleus state is defined as the expectation value of Q0 in the substate of maximum M. That is, QA is equal to expectation value of Q0 in the state when J is equal to, in the state J under the condition when M is equal to J. For bare neutron and proton, the electric quadrupole moment is 0. So any measured non-zero value of Q must be due to the orbital motion. For bare, it means for neutron and proton, the electric quadrupole moment is 0 because their neutron doesn't have any charge and proton is isolated. So any measured non-zero value of Q must be due to the orbital motion of protons. As for any nuclear state with J less than 1, Q0 is equal to 0. So observation of non-zero quadrupole moment in deuteron implies that L is greater than or equal to 1, which is the direct evidence for 3D1 component in deuteron ground state. So in this slide, basically what we have learned is that experimentally deuteron is found to have some quadrupole moment, and from our quantum mechanical theory we know that for any state with J less than or equal to 1, quadrupole moment is 0. So it means in order for the deuteron to have quadrupole moment, its J value has to be greater than 1. That is, L value has to be greater than or equal to 1. So it indicates that the possibility of L is equal to 2 in the ground state of deuteron is very much, and it's a direct evidence of L is equal to 2 component in deuteron ground state. Now, nuclear force strong interaction. So we are continuing with our discussion about the spin and parity of the deuteron. Now Q0 is not equal, Q0 is not equal to 0 in 3D1, a direct proof of non-central tensor term in nuclear interaction. It means, as we have seen when we have started our discussion about the ground state properties of nuclei, we have seen that deuteron has a small amount of quadrupole moment. Since quadrupole moment is a measure of non-uniform distribution of charge inside the nucleus, so non-zero quadrupole moment indicates that there is a non-central component in the nuclear interaction. In calculating Q0, the biggest challenge is to get a proper D state wave function. Now we have seen that L is equal to 0 cannot give the quadrupole moment, because L is equal to 0 is when the nucleon is in the s orbital. So s orbital is assumed to be spherical symmetric. It means the charge is uniformly distributed. But since the deuteron has the quadrupole moment, so it will have the non-zero L value, and the best possible non-zero values we have seen that it comes from the D state, for which L is equal to 2. But in order to calculate the amount of involvement of D state in the ground state of deuteron, we need a proper D state wave function, which is difficult to get. Calculations using D state wave function obtained from realistic phenomenological potential suggest a few percent mix of D state wave function in the ground state of deuteron. So people have tried certain wave function, certain D state wave function, which they have gone from realistic mean phenomenological potentials. So when they used, they basically use some realistic phenomenological potential and solve the quantum mechanical problem, and then found out the eigenfunctions, and those eigenfunctions, when they used in the calculation of contribution of D state wave function in the ground state of deuteron, then they found that the contribution is very small, of few percent only. Scattering experiments using deuterons as target give D state admixture around 4%. This validates our calculations drawn from the value of mu and q. So scattering experiments, from the scattering experiment, we have measured that what can be the contribution of admixture of d state in the ground state of neutron, and it comes out to be around 4%. So which basically strengthen our conclusion drawn from the theoretical calculations, drawn from the value of mu and q, measured value of mu and q, that the contribution has to be very small. Accurate d state wave function is essential, as the mixing of L value in neutron is the best evidence of the non-central character of the nuclear force. So it means it is very important for us that we should have the accurate d state wave function, because if we want to know the precise value of how much mixing of d state wave function is there in the ground state of neutron. Nuclear force strong interaction. So while up to the previous slides we have learned that neutron is having the mixed components in the ground state, and neutron is having 1 neutron and 1 proton. Neutron is a 1 neutron 1 proton system. It is the simplest system. So going by that study, in this slide we are going to discuss the nature of nuclear force. So nuclear interaction, unlike others, is a complicated function of various terms. So there are various terms in nuclear interaction. The first term is the central component, which is the dominant term and represented by VCR. It doesn't have any theta or phi dependence. It means the main component in nuclear interaction is the central component. Second term is the spin component. Spin component means the nuclear force depends upon the spin also, spin of the nucleons. So it's a function of S1 and S2, and this we can conclude from our observation that E for neutron with parallel spin, its neutron-proton, is not equal to E with neutron with antiparallel spin. So not all combinations of S1. So it means the first term is the central component, which doesn't have any dependence of theta and phi. The second term in the nuclear interaction is the spin component, which is a function of S1 and S2. Not all combination of S1 and S2 are allowed due to parity and time reversal symmetry property of nuclear interaction. Allowed terms include S1 dot S2 and S1 square dot S2 square. Now parity change, what is the meaning of parity change? That is, when R is changed to minus R, angular momentum is unchanged. Time reversal symmetry means when T is changed to minus T, angular momentum changes. That is, motion is reversed. We are discussing the various components in nuclear force or nuclear interaction. Now in this slide, we are going to discuss the possible component of spin term in the nuclear interaction. Now as we have seen in the previous slide, not all combination of S1 and S2 are possible. The only possible components are S1 dot S2 and S1 square dot S2 square. So in this slide, we are going to find out what is the expectation value of S1 dot S2 component. So here some calculations have been shown that S is equal to S1 plus S2. It implies that S dot S is equal to S1 plus S2 dot S1 plus S2, which over simplification yield S1 dot S2 expectation value is equal to H bar square, capital S plus 1 minus small s1 plus 1 minus small s2 plus 1. We are continuing with our discussion about the contribution of spin term in the strong interaction. For triplet state, we have capital S is equal to 1. It implies that 2s plus 1 is equal to 3. Expectation value of S1 dot S2 is equal to H bar square 1 into 1 plus 1. Now as small s1 and small s2 is equal to half the spin values. So minus half into half plus 1 minus 1 by 2 into 1 by 2 plus 1, and it comes out to be around H bar square by 4. For singlet state means in which the neutron and proton has opposite spin. Capital S is equal to 0, so 2s plus 1 is equal to 1. So expectation value of S1 dot S2 in this state is equal to minus 3h bar square by 4. So it is clear that when the spins are parallel, that is triplet state, and when the spins are anti-parallel, and in the singlet state, the expectation value of S1 and S2 are different. So a spin-dependent term S1 dot S2 VSR should be included in the potential and will account for different cross-sections of singlet and triplet states. As in our discussion up to now, we have seen that the nuclear interaction consists of few terms or a collection of terms. In the previous slides up to now, we have learned that the most important term in the nuclear interaction is the central term, then the non-central term, and the spin-dependent term, and the third term in the nuclear interaction is, or strong interaction is, the non-central term or tensor term. So in this particular slide, we are going to study something about this non-central term, that what is the nature of this non-central component. Now deuteron has non-zero quadrupole moment, that is ground state is not a pure L is equal to 0 state, which explains that there is a contribution of some L values in the ground state of deuteron, non-zero L values of in the ground state of deuteron. So interaction has a non-central term. So this observation of quadrupole moment is a reflection of the fact that there is a non-central tensor term in the strong interaction. The term must be of the form VR and not VR. It means the term basically is of the form where the R has to be capital, R has to be this vector. As for a nucleon, the only reference direction is its spin. So only terms like S dot R and S cross R, which relate R to the direction of S, can contribute. So going by our experience with deuteron, since in the deuteron the only reference direction is the spin direction, there is nothing else. So only few terms like S dot R and S cross R, which relate R to the direction of S, can contribute. For parity conservation, there must be an even number of factors of R. So it implies that potential must have terms like S1 dot R into S2 dot R or S1 cross R into S1 cross R dot S2 cross R. Nuclear force strong interaction. So we are continuing with our discussion of components of nuclear interaction. So in the previous slides, we have covered that the nuclear force has basically many components. The major component is the central potential or central term. The second component is the spin term, spin dependent term. Third major component is the non-central component or tensor component. So tensor component can be of the form S1 cross R dot S2 cross R and can be written as S1 dot R into S2 dot R and S1 dot S2. So tensor component can be written as VT S12, where S12 is equal to 3 into bracket S1 dot R into bracket S2 dot R upon R2 minus S1 dot S2. Now this non-central component, which is the tensor component, vanishes for singlet as S1 is equal to minus S2. Remember that we are still discussing the components of nuclear interaction on the basis of deuteron. So in this case, in case of deuteron, we have one neutron and one proton. So S1 is equal to minus S2. So in this case, for singlet term, S12 is equal to 0. Now here in this case, we can see that tensor force is represented. So tensor force in deuteron is attractive in cigar-shaped configuration and repulsive in disc-shaped one. So there are two possibilities in deuteron in which the two spins, that is spin of the proton and the spin of the neutron, can be, one is called the cigar-shaped, another one is called disc-shaped. In the cigar shape, the two spins are parallel but one over another. So the nuclear force is attractive, tensor force is attractive. But when the arrangement is like a disk, that is when they are parallel and separated by some distance, then this tensor force is repulsive in nature. So students, let us summarize what we have learnt in this module. The first thing that we learned is that nuclear interaction, unlike others, is a complicated function of various terms. Second thing that we have learned is deuteron ground state is a mixture of S and D states. Third thing that we have learned is from the studies of magnetic moment and electric quadrupole moment, the contribution of D state is found to be very less and it is approximately around 4%. The last thing that we learned from this module, the non-zero quadrupole moment of deuteron ground state is an indication of a non-centered term in the nuclear potential. Thank you very much.